Hello, here we'll look at application of diagonalizing matrices, namely for computing functions of matrices. Functions here mean nice and more precisely analytic functions. And analytic means one having a power series presentation. For example, Maclaurin series at 0, representing function in the neighborhood of 0 with non-zero radius of convergence. The example which we will treat later is, say, 2 to the x. This has a nice expansion at 0 in the Maclaurin-Taylor series, since we can rewrite it as the exponential function with the argument scaled by this constant logarithm, natural logarithm of 2. And then using the Taylor series at 0 for the exponential function with the natural base, we can rewrite it as 1 over n factorial. See, I will call it m, for all m's big or equal than 0. And then the power of the variable, the mth power, which is logarithm 2 times x all to the m. So that can be rewritten as just the power series in the variable x when we take this constant and get it out of the mth power, raising to the mth power. And then this is just a number, and this is the power. And we have to sum all such starting with 0. So let's imagine we have such a nice analytic function and we want to compute the value on some matrix. That would be square matrix with real coefficients. Again, the reasons for that will have to come later. First, how we can do it? Well, we can literally just substitute the matrix A into the power, namely just follow the recipe, compute the powers of this matrix M. It is a square matrix, we can compute all its powers and then multiply by numbers and take the sum. And since the sum is infinite, to make sense of it, we'll have to take the limit. And that's what we can argue will exist. And the reason for the limit to exist will come from a special property of A. So we have to assume something about A. To make our arguments work, we have to assume that it is diagonalizable. So up to some change of basis, up to some conjugation, it becomes diagonal. Let's first look at what we can do in terms of computing values of functions on diagonal matrices. So let's take D to have non-zero entries on the diagonal. What will be this function on D? And I'll just jump straight to the answer, and the answer will be, okay, we apply the function to the non-zero entries sitting on the diagonal, keep them where they are, and that will be the answer. And why is that? Is just a consequence of easy arithmetic of diagonal matrices. So diagonal matrices add and multiply in an easy way. Rules of addition and multiplication are easy. Let's start with multiplication first. Let's imagine two diagonal matrices of the same size. And when we multiply them using the multiplication rule, we will just see that we end up with diagonal matrix again, and on the diagonal of that product, there will be just products of diagonal entries of two factors we had here. That is for multiplying. For adding, we will also have to do addition at some stage computing the function. The same easy rule applies. So if we do have two diagonal matrices and we add them, the result will be diagonal again, and on its diagonal the entries will be just the sums. This is even easier than the multiplication, but they both are very easy. So in particular, when we compute powers, which we have to have computing the value of our function on the diagonal D, when we compute the powers of D, we just see powers of its diagonal entries sitting on the diagonal. And when we compute the sum, so I'll just start computing f of D as I should by multiplying D with itself some number of times. Okay, computing the power, rewriting it as the power, then scaling it with some coefficient, and finally taking the sum, although infinite, but still the sum of diagonal results, and that will be a diagonal matrix again, with diagonal entries, nothing but the function applied to whatever was sitting on the diagonal of our original D. And that's what these entries are. So we have this rule, and again, recapping, diagonal matrices are really good for doing computations with. Even computing analytic functions of is easy. We just do it all at non-zero entries, which are all diagonal entries. How to get the answer for an arbitrary one? Well, not totally arbitrary, but let's assume that A is a good one, namely diagonalizable. So let's assume that we can find diagonal entries, namely the spectrum, eigenvalues of A, put them on the diagonal of D, and then G will be the matrix built out of eigenvectors with corresponding eigenvalues, and that is what is called diagonalisation. But right now it will be a tool for computing the answer for the function evaluated at A, and the answer will involve these ingredients. So the answer will be, okay, compute f of that diagonal middle of effectively compute f on all the eigenvalues of A, which will be these diagonal entries in the diagonalization expansion, and then we know how to do it, and then conjugate it with G, and that will be the result. So spelling it out again, we will have to, assuming now that these D1 and D up to Dn are eigenvalues of A, we have to find f on them. They are just numbers. Assuming that f is a well-defined function, it is a doable task. And then that is a matrix which is still diagonal, which we have to conjugate with G. So why is that? Why is this true? This time it follows from properties of this conjugation operation, of sandwiching something between a matrix and its inverse. So let's start with these basic proofs and then use them to justify this answer. The first proof again is for multiplication. Assume that we take two matrices X and Y and we conjugate them, and then we multiply the results. And looking at what we have G inverse and G sitting next to each other, so they can cancel each other, we can get rid of them, and the result will be what is conjugate with G of the product of X and Y. And in other words, conjugation with G, thinking of the middle term as a variable, is multiplicative. So we can iterate it and get really this formula. So if we to raise this conjugate to some power, it will be the same as if we just get the power of the middle term and conjugate it. So the second property of this conjugation operation is for addition. If we take two conjugates of some square matrices X and Y, conjugates with the same G, we can rewrite the sum of them as the conjugate of the sum. And this is a result of just applying distributivity twice. First we factor out G, and then we factor out G inverse at the other side. And these two properties, which each of them says that conjugation is multiplicative, conjugation is additive. We're looking at functions which are built using these very two operations: multiplication, iterated some number of times, then scaling, which is again multiplication, and then addition. So that is what now we could use to evaluate f at A, assuming that A has this presentation, has this diagonalisation factorization. So then writing what f is, we will have to first, following the recipe of this power series, we will have first to compute powers of this conjugate, and we know what it is, what we can replace it by. So the progression from left to right along this computation will be to get G and G inverse as far from possible to the left and to the right. And that is the first step. Freeing G and G inverse from this m power, taking them out of nth power. Then we can swap the scalar and the matrix. Multiplication by scalars compute with any matrix product. And finally, we have a sum of conjugates of some things. And using this property now, we can rewrite that as conjugate of the sum. And now the middle term in the conjugate is nothing but f evaluated at D. So we got the formula. And that's a practical recipe of how we can compute functions like this function on matrices. And that will be done in the next video, because I'm out of space now. See you later.